Hi, good morning. Last class we have discussed about the splitting field and we have discussed one problem. You have to prove C is a splitting field over R. Now we say a field E is a splitting field over F if E is a splitting field of some polynomials in f of x. Okay, here we have to prove C is a splitting field of R. Okay, so you have to consider a polynomial in R of x and whose splitting field is C of x. Now splitting field of a polynomial f of x means E is a splitting field of a polynomial f of x if E is the smallest field containing all the roots of f of x in f closure. Okay, then here for this consider the polynomial x square plus 1. Clearly this is in R of x and x square plus 1 equal to 0 implies x square equal to minus 1, x equal to plus or minus I. Clearly R of I is the smallest field containing R and I and hence it is a splitting field of x square plus 1. Therefore R of I is a splitting field of x square plus 1. This implies R of I is a splitting field over R. But R of I is same as C. Therefore, C is a splitting field over R. Okay. Now we are going to prove one theorem. Let a field E where F is a subfield of E is a subfield of F closure is a splitting field over F if and only if. Okay, every automorphism of F closure leaving F fixed maps E onto itself. Okay, every automorphism of F closure, this is a map from F closure to F closure, leaving F fixed, that means sigma of A equal to A for every A belongs to F, maps E onto itself, that means sigma of E equal to E itself. Okay, and thus induces an automorphism of E leaving F fixed. That means this sigma induces an automorphism on E leaving F fixed. Okay, so this is a necessary and sufficient condition for a field E to be a splitting field. Okay, that means every automorphism on F closure leaving F fixed maps E onto itself. Okay. So we are proving the first part. Suppose that E is a splitting field over F. We have to prove that every automorphism of F closure leaving F fixed maps E onto itself. Okay. So E is a splitting field over F means what is the definition? By definition, E is a splitting field of some set of polynomial. Okay. So let Fix I belongs to I be this set of polynomials. Clear? So E is a splitting field over F in F closure of Fix I belongs to I. And we have to prove every automorphism of F closure leaving F fixed maps E onto itself. For this we are considering an arbitrary sigma. Let sigma be an automorphism of F closure leaving F fixed. And we have to prove sigma maps E onto itself. That means sigma of E equal to E. Now let alpha j, this is a collection of all polynomials for which E is a splitting field. Now let alpha j belongs to j be the collection of all zeros in F closure of all the Fix I belongs to I. Okay, so this alpha j zeros of Fix. Now we know that for a fixed alpha j, the field f of alpha j has elements of the form. Every element in f of alpha j is of the form. Polynomial is in alpha j with degree. What about degree? Suppose degree of irreducible of alpha j over f is equal to nj. Then every element in f of alpha j is of the form a0 plus a1 alpha j plus a2 alpha j square plus etc. a nj minus 1 alpha j raised to nj minus 1. Okay, where nj is the degree of irreducible of alpha I over f and ak belongs to f. And we are denoting each element by g of alpha j. Okay, so we because for each alpha j we will get an expression of this form. Okay, so we are denoting that expression as g alpha j G alpha j is actually collection of polynomial because A's are varying. Okay. So consider the set S of all finite sums and products of the elements of the form G alpha j. Okay. Consider the set of all sums and finite product of elements of the form G alpha j. So we are considering all the elements of the form G alpha j where this clearly this element become is in f of alpha j. So we are considering all the elements and all the sums and finite products of elements of the form G alpha j. The set S is a subset of F closure and clearly it is closed under addition and containing 0 and 1. Okay. Also additive inverse of each element. Okay, clear. So uh, since each element of S is of the form f of alpha j1, alpha j2, as we are denoting this as g of alpha j, we are denoting this script as j1, j2, etc. So this consists of, okay, this set S consists of elements of the form G alpha j and also consider finite sum and products of elements of the form. Okay, so that means we are suppose this is one product and if b naught plus etc. So this sum also we are considering. Okay, so each element of S is in some f of alpha j1, alpha j2, etc. alpha jr, which is a subset of S. Okay, so suppose we have this element. Okay, suppose we have in G alpha j, we are assuming all these terms are zero. So we get A naught plus A1 alpha j. Okay. Now for the next we may get element like A naught plus sorry B naught plus B1 alpha j. Okay. Plus some B2 alpha j. Okay. Now, if you consider sum of this, then this is again clearly in A naught plus B naught plus A1 plus B1 alpha j plus X. Okay. So clearly this is in F of alpha. This if you take this as okay, this is in F of alpha j. Okay. Now we are considering some alpha i, then some alpha j. Then clearly this is in F of alpha i and alpha j. So that's why we are denoting like this, and f of alpha j1 j2 etc jr is a subset of S. We see that S contains multiplicative inverse of each non-zero element because f of alpha is a field. Okay, thus S is a subfield of E containing all the alpha j belongs to j. Okay, then by the definition splitting field E of fix I belongs to I, we have S is equal to E because we have S is a subfield of E, S is a subfield of E containing all the alpha j. Okay, but by the definition of splitting field, what is splitting field? Splitting field is the smallest field containing uh, all the zeros. Okay, then by definition of a splitting field of a fix I belongs to I, we must have S must be equal to E. Okay, clear? Now, okay. Now what we have to prove? We have to prove thus we get S is a subfield of E containing all alpha j. And by definition of splitting field means what? Splitting field means this consists of all the zeros. Okay, if this consists of all alpha, clearly this all the zeros, and clearly as it is a field, okay, if you consider any element of this that is also in S, thus we get E equal to S. Okay. Thus, we must have S equal to E. Thus, alpha j belongs to J, generate E over F in the sense that taking finite sums and a finite product. So, the value of sigma on any element of E is completely determined by the values on sigma alpha j. Note that the value of sigma on any element of E, every element in this of the form E is equal to S. S is of the form this form. So every element in value of sigma on any element of E is completely determined by its values on sigma alpha j. Okay. If you take L is equal to a naught plus etc. belongs to S equal to E, then sigma L is equal to this one. Okay, sigma alpha 1, sigma alpha 2 belongs to E, therefore sigma L belongs to E. So if you take any linear combination, then that means that L belongs to S. Okay, and finally we get, okay, sigma L belongs to E. Okay, so this proves that sigma maps E onto a subfield of E, because every element is of this form and sigma L belongs to E. That means sigma maps E onto a subfield of E. Now we have to show that sigma alpha j belongs to E. Okay. So what we have to prove? We know sigma alpha j must be 0 of irreducible alpha j over F by corollary 6.2. Okay. Therefore, because this is a 0 of this one, therefore x minus sigma alpha j over irreducible of alpha j f. Okay. So it is a 0 of this polynomial, therefore it is a 0 of this polynomial also. Okay. And now we have, if fi of alpha j equal to 0, then irreducible of alpha j over f divides fix. Hence, fix is equal to irreducible of alpha j over f. Okay. Now, over f here, irreducible of alpha j over f divides fix. That means fix equal to irreducible of alpha j over f into h of x. Okay. Now, irreducible of alpha j over f is actually x minus alpha j into some k of x from here. Okay. Into h of x. That means x minus sigma alpha j divides both fix, for which fi of alpha j equal to 0. Clear? Once again, here sigma alpha j belongs to E. Okay, and sigma alpha j must be a 0 of irreducible alpha j over f. Okay, therefore it is a 0 of x minus alpha j over x minus alpha j. Okay, therefore this irreducible alpha j over f is actually a multiple of x minus sigma alpha j into something kfx. Okay, therefore we can write like this: fix equal to irreducible alpha j over f into h of x, which is equal to this, which implies x minus sigma alpha j divides fix, for which fi of alpha j equal to 0. Therefore sigma alpha j is a 0 of fix, and which is equal to fi of alpha j equal to 0. Therefore sigma alpha j belongs to S, which is equal to E. Thus sigma maps E onto a subfield of E. That means sigma maps E onto itself. Now we are going to prove that sigma is an onto map from E to itself. Okay. So here we get sigma maps E onto subfield of E. Let beta belongs to E, and we have to find an element x belongs to E such that sigma x equal to B. The same is true for automorphism sigma inverse. Therefore sigma inverse is an element of E. Okay. This implies sigma inverse beta belongs to E. Now sigma of sigma inverse beta equal to beta, this implies then sigma inverse beta equal to x. Okay, here. Okay. Therefore sigma is an onto map in E. That is, sigma induces an automorphism on E. Okay, clear? So we have assumed E is a splitting field, and finally we get sigma. If you take any automorphism sigma, then sigma induces an automorphism on E. As sigma is arbitrary, we can easily say that every sigma induces an automorphism on E. Okay. Now conversely assume that every automorphism of F closure leaving F fixed induces an automorphism on E. We have to prove that E is a splitting field over F. For this, let g of x be an irreducible polynomial in f of x having a 0 alpha in E. Now let beta be a 0 of g of x in f closure. Let beta be a 0 of g of x in f closure. Then by conjugation isomorphism theorem, there exists an isomorphism psi alpha beta from f of alpha onto f beta, leaving f fixed. Okay. Therefore, by theorem 49.1, this sigma psi alpha beta can be extended to an isomorphism tau of f closure onto a subfield of f closure. But then clearly tau inverse is a map from tau of f closure to f closure, which can be extended to an isomorphism mapping f closure onto a subfield of f closure. Okay, since the image of tau inverse is already all of f closure, we get tau must be onto. Okay, therefore tau is an automorphism of f closure leaving f fixed. Then by assumption, tau induces an automorphism of E. Therefore tau of alpha equal to beta is in E. Okay, that means tau of an element of E, tau of element E belongs to E, tau of alpha belongs to E, tau of A equal to psi alpha beta of A. For every A belongs to f of alpha. This implies psi alpha beta of alpha belongs to A. Psi alpha beta of alpha is beta. The beta belongs to A. Thus, we have shown that if g of x is an irreducible polynomial in f of x having a 0 in E, then all the zeros of g of x in f closure are in E. Hence, if gkx is the set of all irreducible polynomial in f of x, polynomial in f of x having a 0 in E, then E is the splitting field of gkx. Once again, if g of x ekx is a set of irreducible polynomial in E having a 0 in E, then E is a splitting field of gkx. That means for the corresponding sigma we get a splitting field. Okay, and E is a splitting field of the some polynomial. That means E is a splitting field. Now moving to one definition, let E be an extension field of a field f. A polynomial f of x in f of x splits in E if it factors into product of linear factors in E of x. Okay. For example, the polynomial x square minus 2 in q of x splits in q of root 2 because we can factorize like this. Therefore, this is splits in E if it factors into product of linear factors in E of x. This polynomial also split in q of root 2 root 3 because this you can write like this. Okay, that's all for today's class. In the next class, we will discuss one corollary, also one theorem.